Alright, we've just created some really cool two-dimensional curves. What's left but to try to create some cool three-dimensional curves? And as a reminder, if you're looking for this content, or if you're looking to see what else is out there in terms of three-dimensional curves, these are ideas from chapter 10.7. Okay, so I am going to talk about this curve because it's cool. R of t is equal to cosine of t I plus sine of t j plus t times k. Okay, so this is bringing together a couple of the different ideas from before. Remember what this vector I, j, and k are. These are our unit vectors. This is 1, 0, 0. This is 0, 1, 0. This is 0, 0, 1. So really this equation is the same as cosine t comma sine of t comma t. So this is this is another way to write that vector. It's also breaking down and showing us that f of t is equal to cosine of t, g of t is equal to sine of t, and h of t is equal to t. Right? We have three coordinates because this is a function, this is a vector function in 3 space. So what does this look like? If you just came from the previous video, this should look really familiar because if this were instead, if this were the vector cosine of t sine of t comma 0, well, that looks a lot like the equation we just had. This would be a circle in the plane. This would be a circle in the xy plane. Right? Z is equal to 0. So we're only in the xy plane, so we can ignore z. And we have cosine of t sine of t, so that's just a circle in the plane. So what that means that is if we are looking at this curve from above, so if we're looking from the positive z direction, then it looks like the path that comes out is going around and around in a circle. The path goes around and around in a circle. Okay, so that's what happens if we ignore what the z-coordinate is. So let's just now think about the z-coordinate itself. So think about what z of t equals t brings to the picture. Okay, so if we just had this part, if we just had the z-coordinate, what would it look like? It would look like r of t is equal to 0, 0, t. And so what would that look like? So that's going to stay on the z-axis. But for different values of t, all you're doing is giving us t. So it's like you're following along the z-axis at a constant rate. So this would be a particle that travels along the entire z-axis at a constant rate. All right, so the x and y's are spinning around in a circle, and the z-axis is just going up and up and up and up. What does that make? So putting these together gives a spiral-shaped path. Called a helix. So, whee! Did I draw that right? I think I drew it the opposite way it's actually supposed to be, because you have to spiral around this way on the XY plane. Hello, Springy. Right, so this is a spiral-shaped path called a helix. You've probably heard about the double helix of DNA. Those would be putting two of these together and then connecting them. So let's go over to the computer program. If we're plotting in 3 dimensions, then we don't use parametric plot. We use parametric plot 3D. But it's the same structure where we say what's the x coordinate, what's the y coordinate, what's the z coordinate, and we specify what the domain of t is. And here I'm just saying give me something that fits in the box that's size 2. So if we look at this, it's just going around and around and around in this circle because I didn't give it a z coordinate. But if I specify, and then if I say just give me 0, 0, t, this is that vertical path. Okay, but if we put them together, then we get this helix shape, which is pretty cool. And if we look from above, we get exactly that. It looks like a circle, right? And if we ignore the x and y coordinates, it's just going straight up. So that is a helix. All right, and we can use the manipulate function to watch the point go from the bottom to the top. And here's a little question I want you to explore on your own. What happens if you change the order of the variables? Let me share a couple of other examples from the book, one of which is the twisted cubic. So this is what happens if you use the functions t, t squared, t cubed. So it's kind of like y equals t cubed from this direction, or y equals x cubed from this direction. From the top, it looks like y equals x squared. And from the side, it looks like y is equal to the cubed root. Y is equal to x to the 3 halves. Right? This is just projecting down into each of the different axes. So that's a cool function. Watch the point go. Whee! All right, here's another cool function. This one is called the Trefoil Knot because it's kind of weaving inside weaving in and out of each other, and it's actually a knot. You cannot, if you were to put a rope like this, you wouldn't be able to twist it in such a way that it would come undone. And here's a cool one. This is the toroidal spiral. This is a spiral that that you get from plugging in some sines and cosines, and you can change some of these parameters to get more spirals or less spirals. It would be a really cool bracelet, I think. All right, and I'm going to ask you, please make your own. Make some cool things for us all to see in the class. And I have one last thing that I want to talk about here. And this is going to be an idea that comes up a couple of times. So this is called parametrization. Parametrization. I think there's no E here. Parametrization. All right, so the idea behind parametrization is that sometimes you have a curve in 2D or 3D, that you want to represent as a parametric function. Remember, parametric function is the same as a vector valued function. So that is, you would like to find a vector function R of t is equal to f of t g of t, or f of t g of t h of t that travels along the curve. This is called a parametrization of the curve. All right, and so if you're going to do this, so you might want to be able to do this so that you could maybe do some calculus on the curve, which will be the next topics that we talk about. So if the curve is a nice curve, so we're going to talk about a couple of different types of curves, but if the curve is a nice curve, so if the curve passes the vertical line test, and we're also going to consider the case it passes the horizontal line test, or the horizontal line test, and is represented by a function like y is equal to g of x, and if it passes the horizontal line test, maybe it is represented by x is equal to f of y, then the easy way to parameterize the curve is with the function t comma g of t, or f of t comma t in that second case. The domain of t will be the same as the domain of g or f. All right, what does that look like? It says, let's say you have a function y is equal to x cubed. Then one way to parameterize this function is to say, well, we're going to let t just be the x value of the function. And the reason why we would do that is we would say, oh, if we let x just be the t value, then y, if we plug in x, t for x, we get t cubed. And so this is a point on the curve x comma f of x. So when you have a function where it passes the vertical line test, you can just use that function itself. Right? So similarly, if you had the function x equals sine of y, we can just let y be the parameter t, and we can choose x is sine of t, y is equal to t, is a parametrization of the curve. If this doesn't work, you have to find some other way to parameterize. Find a different way based on the definition of the curve. All right, so that's all about the basics of uh, parametric curves, vector functions, all of those things. Now you're an expert. All right, see you next time.